the Computer Vision Center, Barcelona, and Autonomous University of Barcelona, Spain. His contributions to the field are remarkable, with over 100 published papers and accolades in top international competitions and conferences, including IEEE and CVPR. His work has left an impactful mark, garnering over 40,000 citations and achievements such as top ranks in the global tracking and segmentation challenges. In 2018, he was awarded with the docent title in the computer vision from Linköping University, Sweden. In this session, Dr. Khan will explore the evolution and transformative impact of large multimodal models, offering insight into how these models are reshaping the landscape of AI across domains. Please join me in welcoming Dr. Fahad Shahbaz Khan.
Okay, so thank you very much for the nice introduction. My name is Fahad Khan, and today I'm going to talk about some recent advances in large multimodal models, so to say. And before I moved, so is my screen for the presentation mode, or is also the notes are visible? So then I can change it.
Notes are visible, sir.
Okay, let me just change it. So probably will stop. Just 1 second. I will stop sharing and then start again. Okay, so I hope this is fine now. Okay, so before I move to the technical content, just a brief introduction about myself. So I am a professor of computer vision at Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi. It's one of the world's first specialized universities solely about artificial intelligence. So we have different departments like computer vision, natural language processing, and machine learning, so to say, within this university. I also hold a faculty position at Linköping University, Sweden, where I also did my postdoc and also my research fellowship after my PhD. I did my PhD in computer vision from Computer Vision Center Barcelona in 2011. So this is a research center in Barcelona which is dedicated to different aspects of computer vision. So we have around 75 to 80 researchers working on diverse applications of computer vision as well. So my research area is within computer vision, which is the ability to understand the visual world based on the input from sensors such as RGB cameras or even satellite imagery. And within computer vision, I'm exploring some distinct themes. For instance, how to understand and analyze deep learning neural networks, which are kind of a de facto paradigm in computer vision. And then moving forward within computer vision, my main research area is visual recognition models, which is kind of one of the key aspects of working with computer vision. And recently, I have been interested in exploring large multimodal models, which kind of are derived from large language models from natural language processing and leveraging those into dealing with different computer vision problems. And the applications to my work include several fundamental aspects of computer vision, such as segmentation, detection, and recognition, as well as some X plus AI areas, for instance, AI for healthcare and climate change research as well. Okay, so today I will jump into and talk about this recent wave of generative AI, and I'm pretty sure most of you have either heard about ChatGPT or even use ChatGPT as well. So this is kind of a recent paradigm. We call it generative AI, on which different fields of artificial intelligence have really had a profound impact on. And this all started from this nearest 2017 paper from Vaswani and his colleagues from Google. And the paper title was Attention is All You Need. And basically, what we have been looking into this large language models such as ChatGPT or even the large multimodal models that I'm going to discuss today. Transformers, or which was introduced in this paper, is the backbone, is the key driving factor behind all this surge in generative AI. So this transformer transformer paradigm actually is based on self-attention mechanism, which is very distinct compared to what previous techniques in artificial intelligence, such as convolutional neural networks or even the RNNs, were based on. So in a very simple nutshell, in transformers, we have an encoder-decoder architecture. Originally, it was introduced for machine translation, which means that you input one language and then you get an output into another language. And for this encoder and decoders, we have a series of layers which comprise of this self-attention mechanism. As I said, this is kind of the one of the building blocks of this architecture. And the main components, along with the self-attention, is that you also have a layer normalization and feed forward. And the main difference between self-attention and the convolution operation in CNN is that in self-attention the filters are computed dynamically. So it means that you can compute the attention scores of distinct part of an object. So it kind of helps you capture the global relationship or the interaction between distinct parts of an image. If you can consider or conceptualize dividing an image into different patches and then computing the self-attention scores of each patch given or conditioned to other patches in this image. So in this way, like in a very natural way, you can get, you don't have to go through and process all the information. You can be very selective with respect to computing that information. And you also get a more global relationship capturing mechanism as well in this architecture. Okay, so this was one of the driving factors behind this recent wave of generative AI models. And nowadays, there has been so much happening in this area that it is very difficult to keep track of all the progress. But however, there are some notable factors here. For instance, if we see the progress right now, GPT-4 from OpenAI is kind of a de facto when we talk about language capabilities and also vision capabilities. In addition to that, OpenAI has just released their Strawberry model, which has more reasoning capabilities compared to the GPT-4 series as well. They are also trying to now reduce the model sizes, for example. So we have GPT-4 mini as well, which kind of cost very less. In terms of open source domain, because GPT-4 and for instance, the models from Google are kind of closed weights models. So they are API-based subscriptions required for those models. We also have a parallel stream moving forward, which is based on open weights model, and that was primarily I would say the flag bearer in that case is the models from Meta, which are the Llama series models as well. And in a nutshell, what this LLMs or large language models does is that it is basically the next token prediction kind of an architecture. So given a prompt, so in this case, I give a prompt about write a poem on large language models. The model has ingested during its pre-training such a huge amount of data. So for instance, it has been trained on trillions of tokens of language data or text data that it kind of finds some patterns out of that learned data in order to provide a response. The key thing compared to these large language models and what we have been seeing with decision support systems or in the old era's expert system is that these large language models also have some in-context learning capabilities, which means that there are some emerging patterns that can come or evolve during the processing of these large language models, which is something that was distinct compared to the previous attempts within the AI, where the models were basically more static and thus just provide you the output based on the information that they have ingested. Okay, so NLP is not my main area, although most of my research work these days is basically derived from advances in large language models. However, the focus of today's talk will be about images or visual data or videos as well. And the question here is that all this search in large language models, how does it translate to computer vision or visual data, so to say? And I will start with the application or the main area within computer vision. of visual recognition, which is the ability to recognize object categories in a real-world scenario. And that is something that we humans or primates do very easily. For example, even a small kid has the ability to really understand and recognize different objects within an image or within a scene. However, it is extremely difficult for machines to perform a similar kind of task. So I just give you an example of one such problem within visual recognition. We call it human action recognition. So for instance, on the slide here, you can see that we have some frames from different clips, video clips, and they represent different actions or human activities. For example, walking, jogging, running, boxing, and waving. And the idea is that to develop a computer vision algorithm which can take all this training data with label training data and learn a classifier, and then given an unseen video clip, it will have the ability to predict the correct action category that the human is performing. And way back in 2009, before this wave of deep learning and generative AI, the recent wave, how we people in computer vision used to solve is that we have data sets which were very restricted in this sense, and the idea was just to have a category label per video as part of the recognition. And at that time, the holy grail at that time was that eventually we will come up to a point where, given a scene or a video, we will be able to have a complete description or story of what is happening in this event. So for instance, in this case, the model should be able to predict or provide an output that as the head waiter takes them to the table, they pass by the piano, and the woman looks at Sam. Sam, with a conscious effort, keeps his eyes on the keyboard as they go past. So all the descriptions or what is happening in the visual content, we just get the description out of it. So that was kind of a dream at that time. Now, if we see the recent effort, so this is our work that we presented at ACL, the Natural Language Conference in August this year. We haven't reached, I would say, to that point yet, but we have come close now, just thanks to these recent efforts in large multimodal models as well. So now on the top row, if these are the frames of the video, and if we give this input to the model and ask questions, for instance, can you identify any safety hazards in this video? The model is able to provide a response that yes, there is a safety hazard in the video. A child is playing with a toy car on the floor, and there is a fireplace nearby. So it has the ability to understand what is happening in the video, and also kind of provides you with the spatiotemporal or the temporal aspect as well in the video in terms of how the events are unfolding as we move across time. And most of this, I would say, recent advances is thanks to large multimodal models, which are the counterparts of large language models in vision. So this is how traditionally a vision architecture used to look like, I would say, before, I think, before the last 5 years. So the traditional models, you give an input in the form of an image or a video or any visual data, the model is going to learn something. It depends really what exactly paradigm are you using. For instance, before deep learning, like CNNs, we used to have local features where you just divide an image into different patches. You compute, for instance, in a very simple case, the RGB values of each pixel. That kind of provides you with your feature descriptor, and then you quantize that feature descriptor into a space, get a vocabulary representation, and then you a Euclidean distance to match the feature with respect to the vocabulary that you have computed. So in this way, you can get a local feature representation of this image. Then comes CNNs in 2012 from one of the papers from Geoffrey Hinton, who also, by the way, won the Nobel Prize in Physics this year. And what happens is this, in the CNN, is that now the trend was, okay, we don't want to do handcrafted features and all these engineering mechanisms. We have an end-to-end architecture where you feed an image, you get some series of layers where hierarchical representation is learned, and then it outputs you with a feature representation. And this was the de facto paradigm. Of course, there has been some advances in those that, okay, then later came vision transformers, which again is derived from the transformer architecture in NLP. So you compute the self-attention mechanism rather than the convolution operation. However, in all these different paradigms, one thing was common, was that the input was just solely an image or a video. Now, the recent advances with large multimodal models stems from the fact of also leveraging the language information. So, for example, you input both image and the text prompt, and then the model learns this from this image text pair. So you have a joint representation of image and language information, and that rise to some models which can do zero-shot classification in the downstream task as well. And one of the earlier prominent attempts in this case was also from OpenAI with a vision language model called Clip. Now we can see more fancy models in that space as well. For instance, GPT-4 is also an example of such a vision language model. And if I talk about open source models in large multimodal models, since I am basically from academia, so I mean, I don't have the luxury of thousands of GPUs to replicate what OpenAI is doing, for instance. And so we tend to really try to replicate or do some advances by keeping in mind that the resulting models should be open source and fully transparent as well. So this is one such attempt from people from KAUST University. So they introduced an open source version that mimics GPT-4 in terms of its vision capabilities. So for example, you give an image to this model, you ask a question or a prompt, describe this image, and the model is going to give you an output depicting what it has seen or learned, in this case, in terms of images. And the architecture is very simple. I'm not going to go in too much of technicalities. However, if you are interested in that, please feel free to ask me, and I will explain the things in more technical detail. However, in a very simple, I would say, explanation, if I have to give you, for these large multimodal models, how they work is that you need an LLM to decode the information to language from visual tokens. You also need a visual encoder to get the visual signatures from the image or a feature representation. And with these key ingredients, you basically just need to learn a single projection layer on the basis of image text pairs, so that you can align the large language model. So in this case, the large language model is open source Vicuna, but you can use Llama as well, or you can also use any preferred choice of your model that you would like to have here is that. But the idea is that you have the Q former here is the vision encoder based on the clip features. You have the large language model, let's say in this case Vicuna. You train a single projection layer or a linear layer based on the image text pairs from your visual instruction tuning data as well. So what we do here is that we get some images, we convert them into questions, and those questions were then converted into visual instruction. So a bit of more detailed instructions, like what is happening in the image, what is the relationship of these different objects in the image. And based on this visual instruction tuning data, then you just fine tune the large language model so to adapt it for large multimodal case, or to the case of vision or visual capabilities as well. Okay, so this is what in literature you can find. Now I will focus some of our works that we have been doing in the past year, and how we are advancing, which is basically the main theme of this talk, the large multimodal model research at the forefront of different vision problems. So I will start with first how we can ground large multimodal models to enhance their capabilities in terms of richer semantics, visual semantics, and then how we can also adapt this large multimodal models for satellite data as well. And then if we want to deploy those large multimodal models on mobile devices, how we can do that. In terms of videos, how we can handle the video data, and then the X plus AI applications of large multimodal models for healthcare and agriculture. Okay, just moving to the first theme and current limitation. So if you have probably also worked with or explored GPT-4 V or GPT-4o or mini series, what you can observe is that you input an image, you ask the model about the description of the image, and it can provide you with a holistic representation, what is happening at a holistic level in this image. However, the responses are not grounded. So for instance, if I ask the model, okay, not only describe me this image, but also segment the person in this image, the model does not have the capabilities to do pixel level grounding or the segmentation task along with interleaving with the textual response. And that is the current limitation of large multimodal models that we, in one of the recent works, we explored. And some of the few works that actually do these large multimodal models with grounding capabilities, the problem is that they are restricted to only referring to a single object category. However, we can easily see, even in this room, we have multiple people, and if I want to have multiple objects and do segmentation at one time, those models does not have their capabilities to do that. And then also they cannot do dense pixel-wise grounding, so they can only do region in the form of a bounding box, and also require to specify the region. So I have to really draw the bounding box or tells you the coordinates in order to get the information about the object. So in our recent work that we presented at CEPR last summer, we extended those large multimodal models to also have grounding capabilities. So in this case, you can input an image, a region, or a text. And importantly, you can get as an output not only the textual response, but also you get an output as a text segmentation mask. And to this end, we also have to introduce new task, which is grounded conversation generation and an evaluation framework as well, where we can ground these conversations in the form of segmentation masks as well. So just to give you an example, how does it look like? So in this case, in contrast to how you can work with GPT-4 or any other model like mini GPT, as well, you describe them, you ask, you input an image, you ask the model to describe the image, but importantly, you also ask the model to output interleaved segmentation mask as well. And our model provides you with this output. So here, if you can see these colors, this is basically the segmentation mask which are overlaid over the original image. So this is not an original image. So for example, the red color on the roof is actually the segmentation output for that object class. Similarly, the floor, the trees and all, they are all segmented into different colors. And then importantly, the output segmentation masks are intertwined with the textual output. So in this case, the model is giving output as the image showcase a large white building with a red roof, and it provides you with all the detailed responses. So in this case, we can observe that the model has capabilities to provide a more richer visual semantics rather than just providing a very holistic response in terms or overview in terms of what is happening in the scene. And to do this, we need to have a data. As I said, you need a visual instruction in tuning data for large multimodal models. So we kind of come up with a data annotation pipeline. And importantly, we annotated automatically 7.5 million unique concepts that were grounded in 810 million regions, which has all segmentation masks. So this is a quite huge amount of data. In case if you would like to go into the details of how this was done, I would refer to our CEPR paper and also to our website, which has all these details as well. Okay, very briefly, how this model works. So, of course, you need to have understanding or semantic understanding at different levels, which means that you need encoders that performs different tasks. So if you want to get a holistic representation of the image output, you need to have a global image encoder. And if you want to have a region level output, you also need the capabilities from a region encoder. And then subsequently for segmentation mask, we also need an encoder decoder for grounding the segmentation output as well. So single scene level understanding or holistic understanding is performed by a global image encoder. The region level understanding in the form of bounding boxes is performed by a region encoder. And then the segmentation based capabilities are provided by this grounding image encoder and pixel decoder that works together to convert the visual language projection layers into language and pixel layers or these projection layers, so that we can at the end get a response where segmentation masks are intertwined with the textual output. And then the model can perform a variety of downstream tasks. So for example, in terms of referring segmentation, expression segmentation, where you give an output, given a question, can you segment the balloon in this picture? The model can segment the balloon, but also provide you with a textual response. You can also do a holistic level image captioning by saying, okay, describe the image holistically in detail, and it can provide you with the holistic content of the image. However, if you're interested to go a little bit more in the region level or phase grounding, the model can also have the capabilities. So if you ask in phase grounding, can you segment a phrase in a hot air? So you provide a prompt or a set of tokens, the model has the ability to actually give you a response. Here are some examples. So for example, in this case, again, these are not the original images. These are the output with segmentation masks, which are overlaid on the original image. So we can see, for example, there's a lot of diversity in these examples. For example, in cases of urban scenes, and also in case of a soccer match, some natural scenes in the form of a sea and a harbor, and also some cases where a human is interacting. For instance, a person is having a black jacket and interacting with the food item. Some more examples. So if you want to do it in turn, so you can have, the model has the capabilities to do multi-turn conversation as well. So you can, for example, on the left case, you can ask the model, can you segment Sergio Ramos in this image? And then the model can provide you with the segmentation output. And then if you ask, as a follow-up question, can you segment now the football? The model can also has the capability to do that. And then some more results on region level captioning. So for example, if you ask what is she doing in this image, so not just a holistic content, but also some detailed understanding of the elements in the image, the model is able to provide you with the response that she is using her cell phone while crossing the street. Then you ask a follow-up question, do you think this is dangerous? And then the model has the capability to provide you with an answer saying, yes, it could be potentially dangerous for the woman to be using her cell phone while crossing the street. So she might not be paying full attention to details. Okay, some more examples. I'm not going to go in details. Those are examples are also on the website, and you can also have we have an online demo. So if you want to play with the model, you can do that as well. So here's the link in case if you would like to use the model or get more information about the model. I will quickly move on to the second part, which is how we can do spatial satellite-based LMMs. So for example, remote sensing or satellite data is very different to natural RGB-based sensors in that the resolution is quite large and the object to scene ratio is quite significant. So we can see small objects, we can see large objects as well. And the idea is how we can do large multimodal models for such kind of a spatial satellite imagery or Earth observation data as well. So we introduced again in CEPR the first model for remote sensing, which has capabilities with high resolution remote sensing images. It can answer at image level queries. It can also accept region inputs to hold region specific dialogue. It can also do visual grounding objects in the form of spatial coordinates. And then again, we constructed a instruction tuning data for this case, and the model has the capabilities to provide some multiple images and region level reasoning as well. So this is in a nutshell what the model can do. You can do scene classification, you can do region-based captioning, you can also do multi-turn conversation about spatial, geospatial or satellite imagery data. So some examples, I would say, for example, in case of disaster management, so the right example asking is if the whole road is flooded, the model can provide these answers. As well, in case if you want to have some more information about, let's say, what if give the bounding box of Boeing 747 airplane, the model can also provide you with this option. Okay, now how we can deploy these large multimodal models on mobile devices? So right now, the pace has been frantic, so you can do quantization of large language models or large multimodal models as well. For example, Llama series have now 1 billion models available as well, I think a couple of weeks ago. However, in this work, which we did in the beginning of this year, our idea was to start and pre-train an LLM and large multimodal model from scratch in an open and transparent manner. And the key novelty I would say in this framework is that we have a shared feed-forward design in the form of in this way. So you can see the red circles here. This layer is actually replicated to reduce the redundancy instead of having a specialized or dedicated feed-forward design. And we have multiple such layers in this large language models. And then the idea was if we can have a faster pre-training by having this shared FFN design so that the models can be deployed on a mobile device as well. And we actually showed such a capability. We developed a 1 billion model that was trained from scratch, and we deployed also on Snapdragon and also on edge devices as well. It runs very successfully with very low latency, with good latency capabilities as well. So not going into the details as well, some output from the model, you can do different kind of conversation with the model on your mobile devices. So for example, you can ask what are the ways to reduce the carbon footprint. You can also ask about planning your trip. You can also ask some transportation tasks. And more importantly, you can also ask the vision capabilities. For example, I give this input image to my mobile Llama in my mobile phone. ask about the image, and if I also ask it to write a suitable poem about the scene, it can provide you with this response from this image from a bridge in London. Okay, video elements. How we can do these capabilities? Videos are different than images. They are also a bit more complicated in terms of their understanding. Again, how do we develop these large multimodal models for video? I'm not going to go in details. I would just show the capabilities of such models. So let's see this video. So you can easily get the gist that there is a baby in this image, and I mean, she's doing some cute things with respect to reading it. Now, if I ask the model the same thing, I input this video and I ask the model what is happening, what is funny in this video, and the model is going to provide me with a response um, saying the video is funny because the little girl is seen reading a book while wearing a pair of glasses and a pink shirt. The combination of her glasses, pink shirt, and the fact that she is reading a book at such a young age make the scene amusing and endearing. So the model has the capabilities to understand the visual content in this video. We can also do some generative tasks. So for example, if I have this video in front of me, so this is basically a video about a cosmetic product. And then I will not run the video. I will just say, okay, if I ask the model, I input this model, this video. And if I ask, okay, what is this video about? So first about the content of the video. The model says the video is about a woman applying sunscreen on her face and neck. Then I ask the model, generate a creative advertisement feature about this product that can be used on the product website. And then the model says, gives me a rhythmic, I would say, not bad, a reasonable output with some kind of of an advertisement that can be used for this video or for this product. So that's actually very interesting case. So if the model says, say goodbye to sunburn and hello to a healthy glowing complexion with our new sunscreen product, designed with natural ingredients and a lightweight texture, our sunscreen provides a broad spectrum protection against harmful UV rays, ensuring your skin safe and protected from sun damage. So something very generic. Okay, lastly, I will move to how we can also adopt these large multimodal models for real world scenarios or scenarios where it really requires attention. So I will just give an example of healthcare case. So this is one model that we have developed for specifically for endoscopic data. So for example, colonoscopy is a de facto procedure for any kind of endoscopic in the form of endoscopic exams. Colorectal cancer is one of the leading causes of death in cancer patients. And the idea is how we can have, again, large multimodal model that can provide different downstream tasks. For example, on the left side, we have image classification. On the middle, we have expression comprehension. And on the right side, we have image captioning. So if you ask the model, the human asks the model, identify the correct category of the object, the model can give to you response that it is high-grade dysplasia, which is one of the categories of inflammation in the stomach or also in the esophagus. The model, you can also ask the model some more detailed instruction, questions about the content as well. So this is just how the model works. The demo is also available on the website in case if you want to use it. So the ask was categorize the object, and then it provides with you the option. If you want to have a detailed understanding, you can also ask questions about more detailed captioning part with a given image or a video as well. Similarly, for X-ray data as well, we have such things. So you can ask a given X-ray and ask the model describe the findings and impressions it can provide you. Again, there's a disclaimer. This is not a replacement for radiologist or pathologist or doctors. This is just to aid. These softwares are not products, so they are not FDA approved. These are just solely research-based things, and there is no guarantee that they are going to provide some exact answers for your case. In any scenario, please consult the doctors. This is just as a research purpose, just to show the capabilities we can have with large multimodal models in healthcare sector as well. Okay, this slide will be very interesting because the title is I'm saying current research direction. So even though I was explaining some of our recent works which we published or just very recently, but that is how frantic this research pace is in this area, that whatever I have done 6 months ago probably, will not be relevant in the next 6 months, or, there will be new models coming up. So the pace is crazy in this area. And with this thing about current research direction, what I mean to say is that this is currently what I'm doing, and the plan is in the next 3, 4, or 6 months, to pursue these directions as well. The first direction is I am going in the direction of massively multilingual, large multimodals as well. So right now, most models are English centric. So for instance, if we want to develop models for low resource languages as well, such as, some very regional languages in the Indian subcontinent, let's say, Gujarati or Tamil, or, in our case, Pashto, how we can do that. Some example projects, I'm heavily involved in doing Arabic large multimodal models. We are also developing a culturally diverse set for 100 languages worldwide. And you can see from this example, the red dot means that those countries or languages are covered. So they also have from all continents: Africa, Middle East, Asia, South America, as well. Similarly, I'm also looking into how we can further enrich large multimodal models with respect to their semantic understanding capabilities. So for instance, if you have